Hi, my name is Jiawei. I will introduce the paper Learning by Novel View Synthesis for Full-Face Appearance-Based 3D Gaze Estimation. With the development of deep learning, gaze estimation has made great progress and enables various applications such as human-computer interaction and human behavior analysis. As a general difficulty, 3D gaze estimation training data is hard to collect and impossible to annotate manually, and the diverse illumination conditions and the large head pose range from different environments are difficult to be maintained at the same time. Therefore, instead of collecting a more comprehensive real data set, we tend to synthesize data for training gaze estimation model. As an overview, we start from an existing gaze estimation dataset and do 3D face reconstruction. We rotate the face to synthesize new training dataset. We also propose a new gaze estimation model. By training the model with the synthetic data, it works much better on the target data. For the reconstruction methods, we avoid using 3D morphable model texture because it by default gives a forward gaze and the original gaze information is totally lost. On the other hand, there is another line of methods which directly sample RGB value from the original image. For example, the face alignment tool such as 3DDFA gives 3D face in orthogonal projection relation with the original images. So in this paper, we mainly use these methods for reconstruction. The synthesis process can be summarized as a single image reconstruction which produces 3D facial mesh that is in orthogonal projection with the input match. And the second step is called Projective Matching, which transforms the reconstructed face to a physical space. The purpose is simply to align the face with the gaze label in the same camera coordinate system. After this transformation, using a given camera matrix, the face can be projected back to the original image. Projective matching is to find the position of VC on this back-projected ray V', which matches the perspective projection. The task is to approximate alpha and beta based on the 6 known landmarks and apply this transformation on the whole facial mesh, where alpha is a scaling factor to physical size and beta is the offset between reference landmarks and the VP landmarks. After the projective matching, we can rotate the face and gaze with arbitrary head pose as shown in these examples. However, as is always the case, there is domain gap between synthetic and the real domain. In this case, the rendered images are in black background only, and the reconstructed face has some artifacts in the face outline region because they are invisible during the reconstruction. So we did a background augmentation and proposed a mask-guided model. Background augmentation is to prevent the model from overfitting to its black background. So we render the image to random color and to random scene. Besides, we also render with a lower ambient light for better illumination robustness. Here I will introduce the mask-guided model. Based on the ResNet 50 backbone, we added an extra module for segmenting out the facial region. And the facial region map is multiplied back to the feature such that it gets higher weight. The ground truth mask is obtained during the rendering process, so the model can be seen as a supervised multitask model. In the experiment, we focus on the data extrapolation task. We extend the source data to similar head pose as the target datasets. And in this paper, we mainly use ETH-XGaze and IDApp as the target. Here's the head pose and gaze distribution. The source dataset MPI face gaze is extended to a similar distribution as each target. And finally, gaze 360 is another real dataset collected with a large gaze range. Here's the comparison of gaze estimation error using different training datasets. The proposed synthetic dataset MPI-NV outperforms many real datasets in many cases, especially compared to the MPI face gaze. By extending its head pose, the new dataset effectively reduced the error in the extreme head pose cases, and the mask-guided model also showed effective improvement. For this IDF floating target results, since MPI face gaze and X gaze are both collected using the screen target, the head pose gaze offset range is relatively smaller, as can be seen from this distribution. While for IDF-FT, the floating target is more unconstrained and results in a much larger head gaze offset. Therefore, the Gaze 360 produced the best results due to its physically unconstrained collection process. This shows one disadvantage and the future challenge that the proposed method cannot handle the offset by simply rotating the head. In the previous experiments, we relied on the target head pose distribution to create new dataset, but in this part we consider the situation when we don't know anything about the target domain, and synthesize data by sampling gaze from a Gaussian distribution with different standard deviation. From the test results, even we don't rely on the target domain, the error can still be reduced effectively and reach a similar performance compared to relying on the target domain, which is the dashed line. From IDF-CS, we notice that when the gaze range becomes too large, the performance may drop, but it's still better than the source dataset. Thank you for listening.